So right now I want to talk about section 1.6, the graphs of functions. And this is going to be 3, 7, 13, 25, 29, 55, and 57. So more than usual, but hopefully not too terribly many. The main topics for this section are going to be zeros, increasing, decreasing, constant, even, and odd, and this is for functions. And then we're going to have what I'll call local and global, maxima, and minima. And these are more generally called extrema. Okay, so I'd also like for you to work through examples 1 through 4 in the book. So the zeros, or roots, oh, that should be roots, not roofs, roots, of a function f of x are the x values, so that f of x equals 0. And you notice this is zeros without an e. If I had an e here, that would be the present tense of the verb zero, like to zero in. He zeroes in on the subject. So it's zeros without an e, just a little note. And now I want to discuss behavior of some functions. So I'll make a little table here. So we're going to have what the behaviors are. So we've got f is blank on the open interval AB. That's on. My O got a little funky there. F is what? F is either increasing or decreasing or constant. And this happens if for all a less than x1 less than x2 less than b, something happens, and what is it? It's increasing if f of x1 is always strictly less than f of x2. It's decreasing if f of x1 is always strictly greater than f of x2. And it's constant if f of x1 is always equal to f of x2. And if we were to put less than or equal to signs in here, as opposed to strict less than or strict greater than signs, we'd get what we call non-decreasing or non-increasing. So you might hear me say non-decreasing or non-increasing. That's just if we have a less than or equal to sign, as opposed to a strictly less than sign for these. So let's do some examples. So let's just look at a function really quick. Let's say this is 2, this is 6. My function, let's just suppose it goes up like this, goes over here, and then it goes down. Well, on the interval between 0 and 2, it's increasing, so we do like a little over and up arrow. On the interval between 2 and 6, it's constant, and on the interval between 6 and, say, what is this, I guess 10, it is decreasing. So increasing, constant, decreasing. Okay, so that's just to give you an idea. Let's move on, but I want to move on because my guess is you've heard of increasing, decreasing, and constant before. So let's, and again, like just another word on non-increasing or non-decreasing. So non-increasing means decreasing or constant. That's non-increasing. Non-decreasing means increasing or constant. Okay, so that's all those mean, and you might hear me see those, but these are the ones that you would be responsible to know for class. So let's move on. So suppose a function with domain D, and that a, b is a closed interval that's a subset of D. Further, let's let x naught be an element of this closed subinterval. And we're going to let y naught equal f of x naught. Okay. Now, if y naught is bigger than f of x for all x in the open interval AB, except for, of course, except for, of course, x naught, because y naught equals x naught, then we're going to say that x naught is a local maximum. And you could say, so it's a local maximum. We could say, we might say that y naught's the local maximum. We might say the point x naught, y naught is the local maximum. But that's just to say that this is going to be the local maximum. If y naught is greater than f of x for all x in the entire domain, again, except for x naught, because, y naught can't be greater than itself, then we'd say x naught is a global maximum. Okay, so the idea is that if this y naught is the biggest value that the function attains over its entire domain, then this is a global maximum. If it's just the biggest value that it attains over some open interval, then it's a local maximum. And so you might also hear this called a relative max, and you might hear this called an absolute max. Okay, so just relative is, in this context, relative is another word for local, and absolute is another word for global. So similarly, we define local and global minima. So that's if instead of being bigger than everything, like with y naught less than f of x in place of y naught greater than f of x. Okay, so that's how that's going to go. Now, if we are just talking about a maximum or a minimum, so the generic term, wow. For either is extremum. Extremum. Man, I'm having trouble writing tonight. Extremum. Okay, so let's just take a second and consider a little function. So it's going to go wiggle, 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 and then roll on out. And we're going to assume that this function approaches the line y equals 0 as it goes off to infinity in either direction. So this is going to be an absolute max. So for absolute max or a global max, this is the highest point that the function attains over the entire domain. right? And you can define it by the x value or the y value. I'm not going to be too much of a stickler about it. This is going to be the absolute minimum. Okay, so this is the lowest point that the function attains anywhere on its domain. And again, you could call this a local max, a global max, or a global min. You can also call it an absolute max. You can also call it an absolute min. So this one is an absolute max or a global max. This one is a absolute min or global min. Now, we notice there's a little bit of an issue here. The way that I've defined a local maximum, an absolute maximum is also a relative maximum. All right. Some books will say, oh, if it's an absolute max, then it's not a relative max. But my qualm with that is that it clearly, any absolute max also obeys this. So I'm not going to fuss too much about that. It's just that this is a relative max, but it is not the absolute max. Okay? Similarly, this is a relative min. It is not the absolute min. Here's another relative max. The idea is that these are the high points in a region, but they're not the highest point of the entire function. So that's relative or local versus absolute or global for extrema. This L got a little rough. Relative max. Okay, so what I would like to do now, let's just take a moment and sketch a couple of functions. So this is going to be kind of a strange exercise, but I want you to sketch 3 different functions, and you don't have to write down the piecewise defined thing. Just sketch 3 different functions on the interval from 0 to 10 that are, let's say, increasing on the interval 0 to 3, that are, let's say, constant on the interval 3 to 7, and then decreasing on the interval 7 to 10. So this is going to be kind of like that thing that I did earlier. So just take a second and do this. You can pause the video if you want. I'm going to take a sip of tea. All right, so I'm going to just sketch a few, and then we're going to answer some questions about these in a moment, but I'm just going to sketch a few. So let's have one that goes, so it's increasing from 0 to 3. Actually, you know what I'm going to do? I'm going to kind of cheat, and I'm going to copy this thing a few times so I can just keep using the same picture here. All right, so let's have one that starts at f of 0, 0. It's going to come up a little ways, and then it'll come over, and then it'll come down. So it goes down to 10. That's 7, 8, 9, 10. Goes down here. Let's just get rid of some of that so we don't get accidentally off to 11. Okay, so this you can verify it's increasing, then it's constant, and then it's decreasing. So this is 3, this is 7, this is 10, and here, of course, x equals 0. Okay, now what if we had, instead of that, what if we had something like this, then this, and then this? Let's do fill in this one, leave these others as holes. Okay, this one's also increasing, then constant, then decreasing. Now, what about this one? Increasing, then constant, then decreasing. Okay, and let's, maybe I should just draw some lines between these. So now I want to ask you 3 little questions about these. And your graphs could have looked anything like anything. It could have been just the same thing shifted up and down. I just want to show you that these could look different. Okay, so now 3 questions. Is it necessary that there is a global min at x equals 0? Question number 2. That was question number 2. Well, that's question number 2. Question number 1 was, is it necessary that there is a local min at x equals 0? And 3, finally, flying in the face of number 2, is it even possible that there is a global min at x equals 0? So let's answer these 3 questions. So yeah, darn, I wrote them in the wrong order, but luckily I can cheat, right? This is one of these things that it's horrible that I'm doing this, but man, is it handy. Okay, so question number 1. Is it necessary that there is a local min at x equals 0? So let's sort of highlight the important words here. Is it necessary that there is a local min at x equals 0? And now, just because you happen to get yeses or nos on some of these questions from the 3 graphs that you happen to make doesn't mean it's true for all such graphs, but this is just sketching these graphs is just to kind of get you thinking a little bit. Is it necessary that there's a local min at x equals 0? And the answer is yes, because if I look at anything that's in the range around here that's close, this is always going to be the lowest point. So it's for sure a local min. So the answer is yes. Now the question is it necessary that there is a global min at x equals 0? And I think the first and the third clearly show this is not a global min because it's identically achieved over here. This is not a global min because there's a different global min that's down. Well, actually, there's not a global min, but this is definitely not the lowest point. The reason this one doesn't have a global minimum is because there are many minima that are all the lowest. So there's no, or I guess there's no minimum because it's not ever a lowest point. It's just there's a bunch of stuff that's tied for the lowest. We're not going to fuss too much about that because, again, there's depending on which textbook you look at, people say different things. But the point is, there's definitely not a global min at this point on this function. So is it necessary that there's a local min here? The answer is yes. Is it necessary there's a global min? The answer is no. Now, is it possible that there's a global min? And the answer is yes, because look at this one. Okay, this point has a global min. So the answer is yes. Now, if you're wondering why I'm looking at the minima that are at these endpoints, it's similar to if you're at an endpoint, it's similar to this, except it just looks a little bit funny because x naught is in this closed interval. I'm going to get off into the weeds here, so if you want to stop the video now, you're safe. I'm going to get off into the weeds about some technicalities here. If x is in this closed interval, then for all of the x in the open interval except perhaps x naught, this condition holds, then we've got a local max or min or whichever. So when you're at the end point, then if x naught is my left endpoint, then my AB is just coming out to the right away from it. Okay, so this still works on endpoints, even if it seems like, hey, wait a minute, if my x naught is an endpoint, then it can't be in this open interval. And sure, it's not in the open interval, but that doesn't matter because we're just looking at all the stuff in the open interval around it, okay? So in the case that it's an endpoint, that open interval is just going to be to one side or the other. If that didn't make sense, don't worry too much. That's just kind of getting off in the weeds. This is the main idea. I hope that made some sense, and we'll talk to you.